All right, so welcome everybody to today's special year seminar. So I will be giving a talk today on meta learning. So this is work I did, I guess, 4 years ago, and I just thought I'd switch things up a little bit. I already talked about the more recent work I did in the during last year's workshop. So this is. All right. So first, let's talk about how to actually advance this slides. 1 second. Great. Okay. So first, let's start with what meta learning is exactly, right? So there's actually a lot of different definitions in the literature. Various authors actually, refer to different things as meta learning. So this is my way of actually unifying the different meta learning formulations and to actually give concrete definitions on what we mean by meta learning. Okay, so meta learning is essentially the study of how to use machine learning to design machine learning methods. And so here we have two levels of learning, right? So just for clarity, right, we'll refer to the top level machine learning, right? The machine learning method that we use to actually automate the design of machine learning methods. That is what we call meta learning. Now, the base learning refers to, essentially ordinary machine learning, right? So that is the machine learning, right, we do, right, for the base level. So we need to think about two things, right? And it's clear from this definition, right? So first of all, right, what is the space of base learning methods that we can actually consider? And secondly, what is the meta learning method that we can actually use to search this space? So different meta learning formulations actually differ in the choices of both the search space and the meta learning methods. And we'll talk about a few examples of those a bit later. Okay, so let's talk about the different meta learning formulations. So this is just by going over some of the existing methods that various authors have proposed. And these all methods have all been referred to as meta learning methods. So the most simplest is the regime of multitask learning, right? So in this regime, basically, you can imagine a model where we essentially have a decomposition of the parameter space. So essentially, the parameters of the machine learning model is going to be divided into two parts. So one is data. So data is going to be the parameters that are actually going to be shared across all the different tasks that we'd like to learn. So phi here or psi here is actually going to be specific to each different task. So in this example here, for example, we have two different tasks. And so for task one, we'll use this set of hyperparameter or this set of parameters. For task two, we'll use this other set of parameters. So the base learner here is very simple, right? So we just have a model, right, that takes in an input and gives us a prediction. And so we just have this decomposition of the parameter space into theta and psi. And the space of trained base learners is essentially going to be the following. So, so first of all, the theta, we're going to refer to them as meta parameters, and the psi are going to be the base parameters. So what this is essentially saying is if we take a look at the different things in the search space, we are essentially going to minimize, right, over the task-specific parameters psi, right, to actually train our base learner, right? So this is what the minimization is doing, right? That is essentially just ordinary base learning. And here, so the different base learners we actually consider are the different models where the base parameters are already trained on the task at hand. And the only thing that varies, right, is the meta parameters. And so we actually learn over this space. What we are going to be essentially doing is we are going to be finding, right, the F, right, the base learner that where the meta parameters are actually going to be optimal, right, with respect to the loss that we actually have. So essentially what we do is we are going to be first minimizing over the meta parameters, and then in the inner loop, we're going to be minimizing over the base parameters. Now, of course, this can be actually done jointly. So this is actually as easy as base learning, right? So we can learn the two theta and psi simultaneously. And that is why in some papers, this is actually just not considered to be an instance of meta learning, but rather an instance of base learning. So next we have a slightly different regime of hyperparameter optimization. So that is also considered as an instance of meta learning in the following sense. So we have the same base learner as before, right? So before, remember, right? So theta is the meta parameters, psi is the base parameters. So here we're just gonna rename things, right? Theta is gonna be called the hyperparameters. So the difference is going to be this, right? So we basically have, again, the same space of trained base learners, except that our loss function here, right, can also depend on the hyperparameters data, right? So in this case, you can think of the data as containing, for example, the regularization hyperparameters that you might have in the loss. And so again, after you train this base learner, right, so psi theta star is going to denote, right, what the optimal base parameters are given the hyperparameters. So there's another difference between this setting and the previous setting, and that is we actually have two different losses here, right? So we actually have one different one loss function for the base learning and possibly a different loss function for the meta learning aspect. And so, so for example, this could be, you might want to look at the performance on the validation set instead, right? When you are actually doing meta learning. So next we have automatic model selection. So this is a bit less common in the literature. So there have been some papers that explore this idea, which is basically the following. So you can think of this sort of simplified picture, right, where we have, is there a question?
Yeah, can I ask you, can you hear me?
Yes.
Yeah, this is Maury. Just the two things that you showed a second ago, how is that related to, for instance, structural risk minimization? Because I don't see structural risk minimization. Are you familiar with in VC theory?
Right. Yes.
Because I don't see much of a difference. And in fact, maybe that's what you're getting into. I don't see much of a difference between that and model selection.
Yes. So in fact, so this is actually just going over the different pieces of literature where people have referred to their method as an instance of meta learning methods. So there is a lot of overlapping terminology. A lot of things, for example, that are referred to as meta learning methods could be viewed as, instances of other, they could be known by other names. And so one example would be just this multi-task learning, for example. I think multi-task learning is the more common name, right? But then if you take a look at the literature, so meta learning is more of an umbrella term that sort of encompasses all these different flavors of meta learning.
Okay. Because I mean, so far, I'm not sure I'm seeing much differences. I mean, here, you did talk about the difference in choice of loss.
Right.
And is it possible to give another example where the losses might be different? Why one might want to choose different losses, or this is
right. So in this case, in the case of hyperparameter optimization, for example, so one instance would be, whether you're evaluating the loss on the validation set or the training set, right? So that would be a simple case when the base loss would be different from the meta loss. You might be able to think of other examples. I can't actually think of a good one off the top of my head. That is typically, at least in the hyperparameter optimization literature, what people typically use. I guess one other, so I'm going to talk about this a bit later on. So I'm going to be talking about learning optimization algorithms, for example. And then, for example, for the base level, we might care more about the conversion speed, for example, right, of the optimization algorithm. But then at the meta level at the meta level, we care about more the conversion speeds, whereas the base level, we actually just want to minimize the loss.
So a quick point, Gary, this is Rich. So as you said, I mean, the fact that you're looking at different sets is not is a general thing in meta learning, right? Often you have a base set, and then like in few-shot learning, you're typically you have very different classes at test time. So that's another example where you know your loss function, you might use cross entropy, you might use whatever classification you want. Those could be different, but the key thing is the actual sets that you're evaluating on is different.
Yes. Mm-hmm. Okay. So a third type of meta learning is automatic model selection. So this is less common in the literature. Basically what these kinds of methods do is they would try to have, for example, they would enumerate over different possible base models. So for example, you could think of different classifiers or different architectures, for example, and then you would have a meta model, G theta here, that essentially takes in features of your training set, and then that is going to predict which of the base models is actually going to be performing the best on your data set at hand. So this is sort of an example where, for example, you can use G theta to select the architecture that you actually use. Now, there is a key difference between automatic model selection and the previous setting. So if you take a look at, for example, hyperparameter optimization, you are just finding a particular phi theta, you are finding a particular setting of the hyperparameters, right, that you might want to use. Whereas as in automatic model selection, you are actually trying to find a parametric model that gives you, that essentially predicts what the hyperparameters you should use. So essentially, the meta learner here is going to, in this case, just select the model, right, that you want to select. And the psi here is going to be the parameters of all the candidate models. So now if we take a look at the search space, so it is going to be different from before, right? So again, so we are actually going to be selecting, right, the model predicted by the meta learner. And there is also another difference. So this side star here, that does not depend on data. So previously, if you recall, in hyperparameter optimization and in the previous setting, right, psi star always depends on data, right? So depending on what the settings of the hyperparameters are, I might actually end up with a different setting of the base parameters. In this case, though, that is not the case. So we are essentially thinking of just just training, right, all these different base models to do as well as they can, right, using these architectures, right, without caring about what G theta is actually going to be selecting. And then after we have done so, we are going to train a G theta separately, right, that gives us the predictions over which model to select. So the meta learning over the space is just going to be, right, training this meta learner, right, this predictor that tells us which model to select. All right, and finally, we have program inductions. So this is quite different from all the previous methods. So this is actually just taking the view of viewing the space of all learning methods as essentially a special case of general purpose programs. And basically you can view a learning method as a program that takes in the training data and the test example. The test example is your this X here. And then you're just going to have the prediction as its output. So the space of train-based learners now is going to be consisting of all computable functions with training data as inputs. So you can see that naively, if you were to try to do this, obviously it's going to take forever, exponential time in the length of the target program. And so now to find the best program, you will just search over all the possible programs in the space. All right, so we've talked about 4 different formulations of meta learning, and so I just want to go over some of the key design considerations, right? So we could possibly come up with more formulations, and so there are a number of things, right, that we need to think about, right, before sort of coming up with a new meta learning formulation, and these are as listed. So at the base level, for example, we care about, we need to think about, right, what's an instance of the base learning problem that actually we want to consider, right? Do we want to think about that as, training a particular model on a particular data set? Do we want to think of, at that as, training a particular model, right, on, a family data sets, for example? What commonalities exist across the different base learning problems. So this is essentially thinking about whether there is something to be learned by the meta learner, right? So you can certainly come up with examples, right, where there is just no regularity, right, across the different things that you actually want to learn across the different base learning problems. Obviously, trying to formulate a meta learning problem in that context is not going to be very useful. And finally, we also want to think about whether the meta parameters or the meta learner can actually generalize over the different base problems in principle, right? Are the hyperparameters we learn going to be useful for other base learning problems, or are they just going to be specific for the current?
So I have a question. So whenever I see these things, it's sort of just an obvious idea, right? You have a 2 set of parameters or whatever, right?
Right.
What do you mean by design considerations? There's no theory, it's a black box.
Yes.
What do you mean by design consideration?
So this is just, we went over, 4 different examples of meta learning. And so they are.
To me, it all seems the same. I don't even see any difference. So what's the difference? Like conceptually, there's very tiny differences. Is there anything significantly different from 30, 25 years ago, or?
So there is, yes.
Okay, so yeah, can you summarize? Yeah, what's
so essentially, in the early days at least, so people have been primarily focused on this setting where you decompose in parameter space, right? That is, you decompose parameters into the meta level parameters and the base parameters.
Correct.
And so later, actually, I'm going to show optimization-based meta learning, which is actually, you can't actually formulate it that way. So you can't actually formalize it in this framework.
Fine.
So, and then there's also, this is just talking about, for example, if you do want to come up with a 5th formulation of meta learning, for example, right? There are just some formulations that conceptually, at least, will be more plausible or more useful, right, than others. And this is sort of just some of the key axes that you want to think about when you think about a new formulation of meta learning. And so at the meta level, there are 3 things that are good to consider, right? So one is, how large of the search space do you actually want to consider, right? Do you want it to encompass the space of all possible base learners? Do you want it to be more specific, right, to a particular family of problems, for example? Now, how do you actually parameterize this search space, right? Is there a natural way to do it? And if so, is it possible to both capture what you want to learn at the meta level, so you want it to be complete, right? You want it to capture the particular, the ideal sort of setting of the meta parameters that you actually want to learn. And also, you don't want to, make it so big such that search becomes intractable. And then so that, leads to the 3rd point, right? How can we actually search the space efficiently? So this is all philosophical at this point, right? And so later on, so it's going to get more concrete. So this is sort of, the work I did, I guess, 4 years ago. And so this is sort of a different way of looking at meta learning. And so it is basically based on this following motivation. So essentially most of machine learning can be reduced to optimization. And so if we want to learn how to learn, right, so we can learn how to optimize. And so can we actually learn to design an optimization algorithm automatically? So, I would, argue, tongue in cheek, that is the most popular field of machine learning. And here's the proof. I actually stumbled upon this a couple of days ago. And there's this company that shall remain unnamed that's, actually starting up a team on this. So good luck to them. But anyways, so if we take a look at the framework that we actually have, so essentially, if we think about the general structure of optimization algorithms, so we are going to be having, right, these different update formulas, right, that essentially takes in the gradients or the history gradients, iterates, and possibly also the record values, and then that is going to give us the updates, right, that we're gonna use to compute the next iterates. So gradient descent and momentum, for example, can be viewed as different update formulas. And so we're in this work, we are essentially thinking about replacing that, right, with a parametric model, right, and then essentially training those parameters to achieve the fastest conversions. So this is optimization-based meta learning, and that is different from the 4 different settings that I talk about. So more precisely, so we are in the base learner, we actually just have, we don't have a decomposition of the parameter space, right? We actually just have the parameters of the base learner, right? And so it just depends on side here. So when the meta parameters are going to come in is when we are going to be searching, right, for the base parameters. So here, essentially, the optimization algorithm is going to take in the gradient of the base loss, right, with respect to the base parameters. The base parameters are the size here as input. And then whatever we get, right, from that optimization algorithm is going to be used, right, as the final set of parameters, right, that we use for the base model. And the optimization algorithm itself is going to be parameterized using the meta parameters, right? So these are the thetas here. And so the search space is going to be essentially consisting of base learner trained with different optimization algorithms, right? So as we change the theta here, we are going to get a different way of actually finding the size, and then the different size are actually going to be used in the base learners. Okay, so when we meta learn over the space, we're going to be essentially training the optimization algorithm. And so before I go to the next slide, any questions on this and the distinctions between this and the previous formulations? Okay, all right. So here's the concrete setting if we're going to think about how to learn an optimization algorithm. So the instance here is going to be an objective function, right? Classically in machine learning, we typically think of images or sentences, as different instances. Here, the different instances are the objective functions, right? So the objective functions are, of course, going to depend on the base loss function, the base model, and the base training data sets, right? So when we change any one of them, we're going to change the objective function. The training set is going to be a set of objective functions drawn from a distribution, and the test set is going to be a different non-overlapping set of objective functions drawn from the same distribution. So the goal is to learn an optimization algorithm that's, first of all, generalizes to the test sets and also converges quickly, right? Hopefully faster than existing optimizers. And so the meta loss is going to be the cumulative base training loss. So for simplicity, we're just showing this for a single objective functions in the training set, right? So what we essentially do is we're just going to be adding up, right, the objective values we obtain, right, at all the different iterations of optimization. So there are 2 papers that came previously that are the most related, and these are the two. So in Bengio et al. 1991, they proposed learning a formula used to update the model parameters during learning. And in McLaurin et al., they proposed learning the learning rate schedule and the regularization hyperparameters. So the key difference has to do with generalization, and that is going to be a recurrent theme that we're going to talk about over and over later on. So in Bengio et al., the update formula doesn't actually depend on the objective function. So if you think about using that learn update formula for other objective functions, obviously you cannot generalize. And in McLaurin et al., generalization of learned hyperparameters to other objective functions is not considered. And generally, it is hard to transfer over, for example, hyperparameters that depend on a particular architecture of the model. There's also similar concurrent work to ours, and that is this paper called Learn to Learn by Gradient Descent by Gradient Descent. And the key difference is that our work uses reinforcement learning and their work uses backpropagation or supervised learning to learn the optimization algorithm. And I'm going to talk about why we actually made that choice a bit later. Okay. So how do we actually learn the optimizer, right? So, it is the most straightforward way to think about this as just a simple, problem, right? We can just write out what the meta objective is actually going to be, right? In terms of the meta parameters data, right? So essentially what we can do is we write down the meta loss, right, which is just the sum of the, all the different objective values, right, at all time steps. And then we can obviously expand this, right? We can expand all the different size, right, to be it's essentially a function, right, of the previous iterate and to the update formula. And now we can just compute the gradient using backpropagation, right? And then we can just now learn the optimizer using gradient optimization on the meta parameters data. Right, and the psi I denotes the ith iterate of the learned optimizer. Update formula. Okay, cool. And so there's an interesting phenomenon if you were to try to do this. So it's, works great on the training set. So if you were to try to use this optimizer on a objective function that you did see during training, it's actually pretty good. But now if you were to actually try to apply it to a non-seeing objective function, something weird happens. So the curve that I want you to look at is this blue curve here. That is basically this optimizer learned by backpropagation. So initially it did pretty well, right? So the loss goes down and then it's fine. But then later on it diverges, right, rapidly. And so why does this actually happen? So now let's think about a simple example of an optimizer, right, that can actually get you pretty good convergence speeds, but it's not actually going to do what you actually want. So if we consider an optimizer that memorizes the optimum of every objective function in the training set, it also tries to identify which objective function it's actually currently operating on, and then it just jumps to the memorized optimum as soon as it does so. So what is actually going to happen, right? So it's going to converge as soon as the objective is identified, right? It knows which of the training objective functions it's actually dealing with, but then of course you cannot generalize. And so this is actually pretty easy to do, right? To identify which of the training objective functions it's actually dealing with, right? So, so this is like a picture that shows you if, you have 3 different objective functions that look like this, you can have 2 queries, right? So you just query 2 locations and you figure out that, with this query, whether it's the green or the blue or the yellow curve. And then with the second query, you can figure out if you have determined it to be either blue or yellow, you can figure out whether it is blue or yellow. So with these 2 queries, you can just figure out which one of the objective functions you're actually dealing with. And now if you think about this more generally, if you were to try to draw n objective functions from a distribution where each coordinate of the gradient everywhere is equally likely to be positive or negative, even if all the coordinates of the gradient are actually perfectly correlated, in expectation, the learned optimizer can identify the objective function in log n steps, right? Every time you're going to have the positive number of candidates. So you just need log n steps. Now, so that actually causes a big issue, because if we now want to actually prevent overfitting, right? So we don't actually ever want to get an optimizer that actually just exhibits this behavior. We basically need to think about, what we can do actually to discourage that, right? To prevent that. So one option is, of course, when you have overfitting, you can try to increase the size of the training sets, right? Now there's a problem because we only need log n steps, right, to actually identify the objective function. So we actually need to have, so T here is the total number of iterations to run the learn optimizer for. So we essentially need to have log n, right, bigger than T, right? So with this strategy, we cannot actually be better, right, than another optimizer that terminates in T steps. And so we actually need to have more than 2 to the T objective functions in the training set, which is infeasible. Now we can try something else, right? So we can say, what if we were to constrain the learned optimizer to be K Markov, where K is actually less than log n? So this is somewhat unsatisfying because you can't even learn simple optimizers like gradient descent with momentum, right? So momentum is going to depend on all the previous gradients that you actually have, right? And then if you're just going to cut off the history to just a small number, then you are not able to recover momentum. So the last approach is a little bit more subtle. So we actually want to constrain the forward dynamics to be stochastic. And that is the approach that we actually take. It's unclear what this, why this helps, what exactly means. And then, so that is what I'm going to talk about next. So what do we mean by forward dynamics? So if we consider the mapping from the gradients from the previous iteration and the updates to the gradient and the current iteration, right? So essentially this mapping is, is trying to predict, right, what the next gradient is going to be, right, from the previous gradient and the update that we actually apply, right, to the iterates. So of course, this reminds you of the Hessian, right, in the limits of infinitesimally small updates, and so that is essentially what the Hessian tells you, right, how the gradient is actually going to change, right, in response to an infinitesimal change to the parameters. So now, if we are actually given the objective function, the forward dynamics is deterministic, right? Because we know exactly what the objective function is. And so of course we can, it's, for example, if you're trying to train the optimizer, you can collect as many samples as you want, right, from this function. And then, you would get, you will be able to use that, right, to actually find the optimal updates that you can actually apply. Now that sounds great, but then if you now think about what actually happens at test time, right? So this is when you get a new objective function, right, that you've never seen before. So you have to have a forward dynamics that is actually stochastic, because you don't actually know what the objective function that you have. And so you can't actually precisely predict what the current gradient is from the previous gradient and the update, right? So the uncertainty is going to be essentially coming from the uncertainty over the objective function that your learn optimizer is operating on, right? So if you think about, I guess this is at a more philosophical level, if you actually knew what the objective function is, then optimization becomes really easy, right? Once you identify the objective function, you can just get to the optimum, right? And the hardness really comes from this uncertainty, right? Of you know, how good is your local approximation, right, to the true objective function. And so, you know, you can already see there's a problem, right? There is a mismatch between the meta training and the meta testing conditions, right? So when we're training, right, so we have the objective function, and then we can compute the Hessians, we can, you know, do all sorts of things we want, but then at test time, we don't have that, right? So we don't have the Hessians at meta test time. We don't know what the objective function is, and then there's just going to be inherent uncertainty, right, in the forward dynamics. Any questions about this point? No, okay, cool. So there's a natural way around this, right? So you can try to make the forward dynamics stochastic at meta training time as well, right? So it's essentially trying to, you know, make the problem harder, right, for the meta learner to try to, you know, get, you know, adapted to the condition where it's actually going to be used at test time. So how do we actually estimate the forward dynamics, right? So it's kind of weird in this case, if you think about it. We actually do know the forward dynamics, but we actually want to estimate it, right? So, and the only reason why we want to do that is because we want the test time conditions to match the training time conditions. And so if we're given the history gradients, right, of all the gradients that we've seen, you know, in the past, then there's no uncertainty at all, because the objective function can be uniquely identified, right? So we're back to square one, right? So we have the original problem that we had before. And so we have to be Markovian in order to actually make the forward dynamics stochastic, right? And so here I want to know the following, right? So even though the forward dynamics is Markovian, right? So, you know, we only have dependence on the previous gradients, you know, up to a certain you know, window. We don't have access to the gradients outside that window. The learn optimizer is not necessarily Markovian. So the update formula here can, for example, still depend on the entire history of gradients, right? And so even though the forward dynamics, right, only depends on fixed you know, size history. Any questions? Okay. So now if we recall the original formulation, right? So this is this original formulation where we just you know, try to learn the meta parameters by you know, gradient descents, right? So that is this setting where the meta objective is going to be the loss values, right, over all time steps. And so then, right, the psi i's, right, so that's the ith iterates, right, is going to be you know, given by the update formula, right? The previous iterate plus the optimize the update formula that we're actually learning. Now, in the new formulation, it is going to be different. So in this case here, so we are going to have, so now first know the difference, right, in the objective. So we're going to have an expectation here. So this is an expectation, right, that is taken over the difference. Okay, so maybe actually I'll go over this part first. So if you now take a look at the updates, right, so this is just rewriting the previous formula, right, so we're just calling this part delta psi. And so what's interesting though is this part. So we are actually going to be sampling the gradients from this probability distribution. So what is this probability distribution? So if you take a look at this part here, right, so what it essentially says is, now given the previous gradients and the updates and the objective function index, right, so this is, we're looking at the jth objective function in the training sets. So this is the probability distribution over the current gradient, right? So this probability distribution is just going to be a delta, right, centered at whatever the current, you know, whatever correct gradient is, right, given these three things. So this thing here, that is going to be a prior over the different objective functions that we actually have in the training sets, right? And then so we're just going to marginalize over over this distribution here, right? So what we are actually sampling, right, is essentially you can think of it as we're pretending that we actually don't know what the objective function, like which objective function it is that we're actually looking at. So we don't actually know it is the jth objective function, right, that we have. And then instead we're going to take this marginal distribution, right, marginalize over the j's, right, over all the different training objective functions. And then we're just going to be drawing a sample, right, from that distribution. So this is different from before, right? So before, so this thing now is going to be being fed in, right, to the different, to the update formula that we have, right? So this is the neural net that takes in your history of gradients, right? In this case, the sample gradients, right, from this, that is going to give you your updates. Whereas previously it was just taking the actual gradients, right, from the objective function at hand. Now the expectation is going to be taken, right, over all the different samples they can possibly have, right? So over all time steps. And so that is essentially what we'd like to solve, right? So we'd like to solve for the theta, right, that actually minimizes this objective. Any questions? Cool.
So is this, you can think of it as some kind of a learned adaptive gradient kind of method?
Learned adaptive gradient, yes. Yeah, so it is learned in the sense that you are fitting the, right, you're fitting the meta parameters data, right? Now the adaptation part, that's just coming from having access to the history.
Right.
Right. Okay. Cool. Let's see. So now we so this is sampling from the forward dynamics model. So this is essentially the forward dynamics model that we have. Right. So now there's an issue, right? So computing this expectation is intractable, right? Think about how many trajectories, right, we can actually have, right? Even in the discrete case, it could be 2 to the t, right? And so computing this expectation is just intractable. And this problem arises a lot, right, in reinforcement learning. So we can try to use off-the-shelf reinforcement learning methods for this. Doesn't solve all the issues, but I'll talk about that later on. Okay, so background on reinforcement learning. So here, the goal is to essentially of reinforcement learning, right, is to solve this optimization problem, right? So here the objective is going to be an expectation taken over all possible or all sequences of states and action pairs, right? So we have initial states, we take an action, we get to the next state, et cetera, et cetera. We're going to be taking an expectation with respect to the joint distribution over all these things. And so this is the joint distribution that we have, right? And so the pi here, right, it doesn't actually appear here, right, it's appearing here, right? So the pi is gonna be the policy, right? What the policy is essentially it's this conditional distribution, right, that gives you, so this, so that tells you what to do, right, at time step t, given the current states, what your action should be. And so in general, it could be deterministic or stochastic. And so now if you were to now take the expectation with respect to this distribution here, and now you think about the cost that you actually can accumulate, right? So at different time steps, depending on the states that you actually get to, right, this cost function is going to assign, right, some score, right, to the different states that you actually want to get to. And so intuitively, the goal is to find a policy, right, such that you get to the good states. So what's most difference about reinforcement learning is that the dynamics are stochastic, whose distribution is not known a priori. So you don't necessarily know the distribution of this, and so you hope to be able to either in a model-free reinforcement learning, just estimate this from samples, or in model-based reinforcement learning, you actually want to fit a model right to the samples, and so this is the key difference here, right? So I want to highlight this expectation here, right? So again, it is over an intractable it is an intractable expectation, right? So there are just exponentially many sequences that you can actually have, right, in this expectation. Okay, so the reduction to reinforcement learning is the following, right? So let's think back to sort of the structure of optimization algorithms here. So we can naturally map the different things, right, to different objects in RL. So first of all, the states, right, could be just the iterates, right, and possibly some features. The action is going to be the action, or sorry, the update that you actually apply, right, to the iterates. The policy is going to be this update formula, essentially, right? So the neural net that tells you, for example, given the current gradients, what your iterate or your update should be, and the cost function is essentially just going to be your objective function. All right. So before we get to the empirical findings, any questions about the formulation? All right. Cool. So I'm not going to talk about the specifics of the RL method that we use because it is sort of, you can use any RL method that you want, right, for this problem, and then a lot of the times the particular choice just depends on which one actually works out the best empirically. So in terms of the empirical findings, so let's take a look at, first of all, the setting that we actually have, right? So the training set consists of one objective function in this case, right? So that is just the cross entropy loss function for training a neural net on MNIST. And so it's kind of weird, right, that we only have one objective function, and then how can you actually train an optimization algorithm using a one objective function? So the reason why we actually have this is because we are making a coordinate-wise assumption on the update formula. So that is the update formula is the same regardless of the particular coordinate. So which coordinate of the parameters you're actually looking at, the update formula is always the same. And so essentially, now you can think about the distribution where you marginalize over the different coordinate choices, right? So you still get a distribution, a thermodynamics model that is not deterministic. The test set here consists of the loss functions for training neural nets for different architectures on different data sets. So in other words, the optimization algorithm is meta-trained on the problem of training a neural net on MNIST, and it is meta-tested on the problems of training neural nets on other data sets. So first, let's take a look at a simple setting, actually. So this is a simple two-dimensional logistic regression problem, right? So it's convex. And so this is just visualizing the trajectory that it's able to find. So this is, we trained the optimization algorithms on, I believe, 100 different logistic regression problems. And now we're going to be visualizing what the different iterates are right in the parameter space. So here we can see this these red arrows here, right, correspond to the different updates that you do, right, to the different updates of the learned optimizer. The other trajectories here correspond to other optimizers. So this blue one corresponds to gradient descent. Momentum is this one, that's LVGS, for example. And so you can see that the learned optimizer is basically, it is taking a larger step sizes, right, than the other methods. And also, it's actually initially overshooting, right? So compared to the other ones, but then it's somehow able to figure out that it has gotten past the optimum, and so it's able to turn around. So we have another example here. So these are all unseen test objective functions, right? So the learn optimizer hasn't seen these ones during training. So this is another one where all the other optimizers are essentially, they're suffering from vanishing gradients, right? So the gradients are really small, and so you need a lot of steps, right, in order to reach the optimum. And so this is what the learn optimizer is actually able to achieve.
So sorry, quick question. So could you say a little bit more about what exactly is being meta-optimized or meta-learned in that phase, near early phase, so that it applies in the test time? I don't quite get what the, what are the, a little more about how that's working here.
Yes, let me actually go back to the first slide here. So basically, yes, no, that's not this one. Right, so what is meta-learned here is this update formula, right? So essentially your theta, right? So that is your meta parameters, right? That is going to control how you actually perform updates, right? To the
So I'm asking though, in this particular case, what are your thetas?
Oh, what are the thetas? So
Yes.
those are just the NeuralNets of a neural net that gives you the updates to the iterates of the base model.
So wait, so when you're doing meta, so in the MNIST example you're talking about, so you're learning on MNIST and you're testing on, let's say, CFAR 10. Right. So what exactly does that mean? Are you, during meta training, you're training up the parameters of a neural net? You're going to use the same neural net at test time? Or what exactly, how is this being?
Okay. So on MNIST, for example, so you would have a neural net, right, that gives you your updates, right, to the, okay, so actually you have two neural nets, right? So one neural net is the base model. So that is just the model which does MNIST classification. You have a second neural net, so that is the meta model. That is the neural net that actually gives you the iterates, and the iterates are the iterates of the parameters of the base model. So initially, for example, you can think of the simplest setting, right? So this meta model, right? Maybe it is just gradient descent, right? So it's just going to take in the gradients, of the classification laws with respect to the base parameters. It is going to just, scale that, right? And then use that as its prediction, right? And then so that just reduces to exactly applying gradient descent, right, to train your base model.
Okay, but what did you actually do?
Sorry?
So it's not so in the experiments that you're showing now, if you say a little more about exactly what was in the parameters of the base model and what was being trained in what was the second model, what are the iterates of the second model here? How are you updating the iterates, for example, from CFAR 10 based on what you learned from MNIST?
Oh, I see. Okay. So in this case, we make this assumption, right, where the updates to every coordinate of the base model is going to be the same function, right? So the update formula itself, right? So I'm calling it the update formula. Is really the meta model that gives you the updates, right? So the meta model is its output is not going to depend on which of the coordinates of the base parameters is actually looking at. So we're really, yes.
So I'm still not getting it. So you're training on MNIST and you calculate gradients, I imagine, to train that net.
No, he's doing it on a per coordinate basis, I think.
But a per coordinate basis, meaning you're just computing updates on a per coordinate basis, not based on gradient information?
Oh, no. It is still based on gradient information.
Okay, so how do you then, so given that gradient information, what do you do now?
Okay, so given the gradient with respect to the base parameters, you have this model, right? The particular model is going to take in the gradients. It is going to give you the updates to the parameters of the base model.
okay, so you have a update that could, so it could be your standard momentum update with a learning rate. There could be some parameters. You're saying that you're going to have some set of parameters that would typically be called like hyperparameters. So how is it different than regular hyperparameter optimization? How can you compare it to that?
Right. So regular hyperparameter optimization, for example, you would try to find a learning rate schedule or a way of scaling the magnitudes of the different gradients, right, with respect to the different groups of parameters, right? In this case, you don't do that. So you're actually taking in the gradients as your inputs. The output could be modifying the direction, right? So the output of your model is going to be depending on like what the neural net chooses to learn, right? You could take in the history of all the gradients that you actually have and give you an update, right? That is different, right? From either the current gradients or the previous gradients.
Okay, so in your case, you took in the input to the second model that was going to determine your update was the current gradients. Can you say anything else about what the other inputs were to that model that's going to predict your update?
Okay. Right. So the other inputs are the current gradients, the previous gradients, the iterates, and the objective values. So I have the illustration here. So you just have these three things, right? So from the beginning of the optimization algorithm to the current time step, right? So you feed in as inputs, right, to your update formula, right? Three things, right? So the current iter or the iter at that particular time step, the objective value at that time step, and your the gradient at that time step.
I see. Okay. And do you have a sense of what it's actually learning there as how it's combining those various things and computing the iterates, comparing it to things like momentum or other types of approaches?
Right. So it is, hard to interpret like, what the weights of the neural net actually mean.
It's sort of the weights, but the outputs, right? So the behavior.
Yes. Yeah. So the outputs, this is what we're comparing here. So these are the outputs that are given by the learned optimizer, right? That is this, this update formula phi here that we are learning. And so these other ones, right? These are the, the standard classic optimizers that you have.
Yeah, it's a little different. You're showing the actual behavior of it. I'm talking about saying, what is its input-out behavior? Given these kinds of past the inputs to that model, what does it produce as an output relative to what you'd get if you had momentum? Just so. Anyways, I'll stop talking. Keep going.
I guess, okay, so you could visualize the comparisons here, I suppose. So they are all starting from the same, same iterates, right? So if you take a look at just the first arrow here, that is a difference between the outputs of the learned optimizer versus this is like conjugate gradient, for example. Okay. So, right, so this is in the 2D setting, right? So I guess, just empirically, it's able to learn interesting behaviors, right? So it's, it is sort of learning to correct itself, and then it's also learning to speed up, right? If it encounters, vanishing gradients. So this is an example where, we actually took the model or the optimizer that is trained on the problem of training on MNIST and apply it to the problem of training on Toronto faces. And so this is what we get. So here the red curve here is our methods. The blue curve is the method trained using backpropagation. And these other curves here are the classic optimizers that you actually have. So this is essentially, showing you that, so this is the at meta training time, right? It has never seen the Toronto faces data set before, right? So it's a completely unseen objective function. And so you can see that the learned optimizer is doing quite well, right? In most cases. So if it's actually, diverging a little bit, it's able to learn to recover. Whereas if you try to train it using backpropagation, for example, you wouldn't get this behavior. So having once it starts diverging, it just keeps diverging. And so you have like the other optimizers here. So this is momentum, for example, and then that is standard gradient set. We can also try it in the setting where the gradients that we actually provide, or the gradients that the learned optimizer is going to see at meta test time, right? So, on the unseen objective function, the gradients are actually going to be a lot noisier than what you actually have ordinarily. So in this case, we essentially just reduce the mini batch size by a factor of 10, I believe. And so this is essentially what we have. So of course, the learned optimizer is not initially it's not doing so well, right? But then it learns to recover quickly, right? Reason why it's not doing so well is just because at meta training time, right, it's seeing larger batch sizes, so a lot less noisier, lot less noisy gradients. Whereas, for example, if you see this, optimizer trained using backprop, that can diverge pretty quickly. Longer time horizon, so this is just at meta training time, we only train the optimizers for 400 iterations, and then at meta test time, we're now applying that for 800 iterations. And the interesting here is just it doesn't diverge, for example, right after 400 iterations. Any questions? All right. So now I'm going to talk about some of the.
By the way, what was your model for combining the past information? Like how difficult is that model? Like, is it a simple model?
It is a simple model. It is a LSTM. Yeah, depends on.
But like, what's the LSTM architecture?
It is straightforward. So I believe a single LSTM layer. I don't even, I can't remember off the top of my head.
Oh, so if it's a single layer, it's almost just like linearly combining or something.
Yeah, but it does have, it does have activation function.
It does have activations, but yeah, I see.
Right.
So yeah, so a lot of the other things are just linearly combining information, and you're doing slight non-linearity of the past information.
Okay, so some of the open challenges, in the setting. So the most important one is just reinforcement learning is hard, right? So our method is constrained by the reliability of the underlying reinforcement learning methods. And it is in a sense not the fault of RL methods. It is just coming from the problem formulation, right? The expectation is just intractable, right? So if you're gonna try to have a policy gradient estimate of this, then it's just going to have high variance. And it is an open question on how to overcome that. And belief, drastically different techniques might be required. And so that's sort of the key open challenge. And so that also means that if you were to use this, methods, there is, first of all, empirically, there's a lot of tweaking involved, and also it's for some objective functions. So for some trainings of objective functions, for different choices of the training sets, you might need to tune your RL method differently, which is annoying and frustrating. And so that's just coming from essentially the unreliability of RL methods, which is a result of this intractable expectation. The second problem is modeling the forward dynamics needs at least quadratic space, right, in the dimensionality. And so that's just because, again, so you're trying to predict what the next gradient is going to be, right, which is the dimensional from what the current gradient is and what the current update is. And so you just have to have quadratic quadratic space. And so, of course, you can try to make assumptions and say, maybe we want to have a diagonal assumption or something, but then, this sort of limitation just, so that's a modeling assumption that may not or may not be accurate. And then if you don't want to make that assumption, then it is difficult to scale meta learning to higher dimensional problems. And so the approach that we took in that particular paper was to train the optimization algorithm on low dimensional problems and apply that to high dimensional problems. And so, I mean, there's an interesting modeling question here. And so that is, so we did make a coordinate-wise independence assumption, right? So, so this is essentially saying, for every iterate or for every coordinates, right, of the base parameters, the behavior of your update formula, right, is going to be the same regardless of which coordinate you're actually looking at. It is not such a bad assumption if you think about, for example, a lot of methods that are only coordinate-wise, right? So, adaptive gradient methods, for example, most of the time you would only the updates, right, to a particular coordinate would only depend on the history, right, of the gradients in that coordinates. But then obviously, like, you hope that you will be able to do something like second order methods, and then that's a setting where obviously this assumption wouldn't hold. And so a question is basically, is there a better way to actually use neural nets to train on, let's say low dimensional inputs and then apply that to high dimensional inputs, right? So what's the right, modeling assumption that you want to make there, right? That's both going to allow the different coordinates, right, to essentially interact, right? But then also you can actually apply them, right, to variable dimensional inputs. Yeah, so that's basically that. Any questions?
Nice talk.
Oh, thank you.
Yeah.
Did I answer your questions regarding the?
Yeah. That's fair. Very good. All right. Thanks a lot.
Okay. Thank you.
Yeah, thank you.
So let me just make a general announcement. So starting next week, or actually next week, we won't have the seminar. So the 2 seminars are canceled because of the workshop.
Okay, can I ask a quick question? The workshop, Kelly,
Yes.
the workshop is the entire week?
Yes, I believe so, yes.
Okay, because we have this reading group and we were supposed to have a meeting on Tuesday at 3 p.m., 3:30 p.m.
Okay.
So we probably should cancel that.
Yeah, that might be a good idea. Yeah. I think, yeah, I'm pretty sure. I mean, I checked Tuesdays and Thursdays, and both days have like speakers. So yeah, it is at least, it's either from Monday to Thursday or Tuesday to Friday. But certainly, I think Tuesday might be a bad time.
Okay. Okay, and who's the workshop organizer? I know that Sham Kakade was one of the organizers, but who could I talk to about the work and after the schedule, or working with the workshop schedule? Do you know?
Oh, it's available on the website. I can send out the link.
Thank you.